Okay, maybe we should start. So, hello everyone. Welcome to lecture number, I believe, 19 of the course. Indeed, lecture 19. Today we're going to talk about measuring DeepNet spectra at scale. So, this is directly related to the recent two homeworks that you were working on. So, a few lectures ago, we started talking about the boomlet of researchers studying DeepNet spectra. And we talked about the phenomenons that occur in the spectra of the layer-wise features and also the layer-wise backpropagated airs. And then what we're going to do today is we're going to answer a question by Amireza. This lecture is dedicated to a question by Amireza, which is how are these observations all related? So we have observations about the layer-wise features, we have observations about the layer-wise backpropagated airs, and today we'll see some observations about the Hessian, and we also saw some observations on neural collapse, right? So we want to collect everything into a single coherent understanding of the spectrum. So we begin by recalling what is the Hessian. So probably all of you know at this point what what the Hessian is, but let me just remind you, this is your chance to ask questions that perhaps would elucidate what you're doing in the homework. I guess sometimes you can solve homeworks without even knowing what is the homework doing, right? I can see myself as a, you know, as a person who's implementing an algorithm. Sometimes you can implement without even knowing what are you implementing. So we have a loss. Homework 8. Yeah. Oh, so you already implemented homework 8 without even knowing what it does. I see. Okay. You know, it shows to the scale of your programming, right? That you can, okay, maybe we shouldn't embarrass Karen. But if you can, if you can implement something, you don't even know what it means. It's kind of like how a mathematician can, prove something without ever going into uh, like mundane details. It's like you can learn about some theorems without ever even knowing about a single application. Anyway, so we have a loss function, which is a scalar, which you can think of as being the average cross entropy loss over your data set. So I remind you that xi's are the examples, y's are the labels, f of xi theta are the logits, and we're calculating the loss over the examples. And then the fundamental quantity that we care about is, the first fundamental quantity we care about is the gradient, which is just the derivative of the loss with respect to the parameters of the model theta. So specifically in the homework, theta would be something like vec of W1, maybe followed by vec of W2, right? And so it's just a long vector, which is the concatenation of all the parameters in the model. And I remind you that theta can also be thought of as a block vector. It's a vector which has a block structure where each block corresponds to a different, let's say a different parameter or a different layer, a different parameter in a different layer. And besides the gradient, we also have the Hessian, which is the second derivative of the loss with respect to the parameters, which is a matrix of size parameters by parameters. And so that is going to be some square symmetric matrix, right? And we care about the eigenvalues and the eigenvectors of the Hessian. So we care about the eigendecomposition of the Hessian. Now, we know that the Hessian is a symmetric matrix, therefore all the eigenvalues are real, and that's it. We don't know, it's not positive definite. So why would people care about the what is the little L loss we're using? So I'm going to be using the cross entropy throughout. Now, you might ask yourself, why are researchers interested in the spectrum of the Hessian, right? One must always motivate a quantity before studying it in detail. So there are two machine learning dogmas that motivate the research of the spectrum of the Hessian. The first is that people believe that if your optimization algorithm converges to a certain place where your landscape, so this is like a function of the loss, this function of the parameters. This is a horrible illustration because your loss function is, theta is 20 million parameters. So if you draw 20 million parameters as a one-dimensional line, it's kind of silly, right? Everyone agrees with that. But that will not stop us from, illustrating what we're talking about. So people believe that if you're doing SGD and you converge, you do SGD step, and let's say at some point you stop here. Now, people believe that if you reach a point which is flat, then your generalization error is going to be good. So flat minima generalize better. So what's a non-flat minima? Imagine if you had something like this and you converge here. This is not flat. Flat on the left, not flat on the right. Okay? So these are dogmas. So just accept it as a belief, Now, the second reason why people are these dogmas in fact true? That's a good question. So I will, in the next few slides, discuss whether they are true or not true. But the answer is, who really knows? Isn't there some intuition to this? Yeah, there is some intuition to this, but I would prefer to defer these questions to the end of the lecture, because then maybe you would be able to even answer your own questions by the end of the lecture without me having to answer the questions, okay? There is intuition for why these people believe in this dogma. Maybe I can present one intuition. So here's what people usually do. Usually people say that the landscape of the training loss looks something like this, and then there is a landscape of a test loss. So they draw another plot like this. Now you can see that there is a shift between the two because the train and the test distributions or data are not the same. There is a slight shift between the two. And then people usually try to say, okay, if your minima is flat, it means that even after this shift, you're still in a flat point. But if your minima is not flat, then you can see a large increase in the loss. But is this a satisfactory answer to Justin's question? Not really. This is just like, what some people would call poetry. It's just, it's words, but do they actually mean anything? Not clear. Is this a satisfactory answer, Justin, or is this a non-satisfactory answer?
I guess I was thinking about like in classical sort of estimation theory, where you're looking at bounds on parameter estimation. You think of the curvature of the likelihood function gives you some information about how good your estimate can be of the model parameter. So I thought maybe there's some connection there.
Yeah,
but
there's definitely connection to what you're saying, and I'll show that in, I think, even the next slide. I won't go into details because that requires going into like, I think PAC-based generalization bounds is kind of what you're thinking about. Yeah. I don't want to dive into that. I have different goal in this lecture, but you're definitely correct. Thank you for pointing that out. Does this flat minima also guarantee some robustness against adversarial attacks? Maybe. I don't think there is. I cannot recall a paper that tried to answer your question, Amireza. But Amireza, you already asked the question that will take us one lecture. You cannot ask another difficult question this way. Let us answer your first question. Okay, so the second dogma, I'm just kidding, by the way, Amireza. Thank you for your question. The second dogma that people believe is that the curvature of the loss is another word for Hessian, is reflecting the optimization speed of SGD. What does that mean? It means the following intuitive idea. If you take a course on optimization, you would learn there that the convergence speed of gradient descent depends on the condition number of the Hessian. So something like lambda max over lambda mean of the Hessian. So, and the intuition is actually very simple. If you're optimizing a function whose level sets look like these, then it's easy to optimize. If you're optimizing a function whose level sets are like this, it's significantly harder, right? If you want to learn, rigorous theoretical statements on optimization guarantees, I suggest you to take a course on optimization theory, convex optimization theory. But again, the idea is that the curvature is somehow related to the optimization speed. And so the closer your Hessian is to an identity matrix, the faster your optimization is going to be. Does that sound like a reasonable idea? Or is it provocative to you? Somewhat reasonable. So let me show you some evidence of people who believe in this dogma. And the first paper is tightly related to Justin's question. So the paper is called Flat Minima, so obviously related. And the paper is by Hochreiter and Schmidhuber. So let's just read a small portion of the abstract. They say, we present a new algorithm for finding low complexity neural networks with high generalization capability. The algorithm searches for a flat minima of the error function. A flat minimum is a large connected region in weight space where the error remains approximately constant. An MDL-based Bayesian argument suggests that flat minima correspond to a simple network and low expected overfitting. So this sentence is dedicated to Justin. Flat minimum, MD, this sentence, right? Because this sentence is, MDL means a description length, maximum description length, if I remember correctly. So MDL-based Bayesian arguments are what Justin was referring to, and this is kind of the classical way of relating the flatness of the minima and the generalization error. But I don't want to dive into this too much. The main idea is that people believe Hessian related to test error. This is what you should take from this. Here's another paper. So this paper is called Sharp Minima Can Generalize for Deep Nets. So this paper is saying that, hold your horses. In fact, so let's read their abstract. What are they saying? They're saying, despite their overwhelming capacity to overfit, deep learning architectures tend to generalize relatively well to unseen data, allowing them to be deployed in practice. However, explaining why this is the case is still an open area of research. One standing hypothesis that is gaining popularity by Hochreiter and Schmidhuber and Keskar et al. Is that the flatness of the minima, so again, flatness of the minima of the loss function found by stochastic gradient descent results in good generalization. This paper argues that most notions of flatness are problematic for deep models and cannot be directly applied to explain generalization. So what they're saying is that, first of all, when you say flatness is related to generalization, you should ask yourself, what is even flatness, right? I didn't provide a definition. So you want to say flatness is defined to be blah. And then if that's the case, you want to show like a correlation of some sort with generalization, or you want to prove some correlation with generalization, right? What this paper is saying is that we can take a network and we can somehow fudge around with the network, just switch something in the network without changing the predictions of the output. And by doing that, we can make the curvature or the minima to be as sharp as you would like. And so what that means is that you can play around with the sharpness without changing the prediction of the network. So obviously sharpness alone cannot be correlated with generalization. Does this make sense? Does anyone have any question? So in short, what this paper is saying is that flatness alone cannot explain the performance of the network on test data. It is, in some sense, a disappointing result, in some sense, yeah. So I think that several follow-up works just tried to define better notions of flatness. So like some notions of flatness you can imagine, like the easiest notion of flatness would be like the maximal eigenvalue of the Hessian. That would be one idea, but maybe that's a bad notion. Maybe you should look at the, the median eigenvalue. I don't know, just throwing something. Maybe you should look at the ratio of the maximal to the minimal. Maybe you should look at the trace. Maybe you should look at the determinant. Like you can invent infinite things. Maybe one of them does correlate with generalization. But again, my point is not to dive into what is the relation between flat minima and generalization. My point is to motivate the notion of, motivate the study of the spectrum of the Hessian, right? Here's another paper. So this paper is called Hessian-based analysis of large batch training and robustness to adversaries. So what this paper says is large batch size training of neural networks has been shown to incur accuracy loss when trained with current methods. The exact underlying reason for these are still not completely understood. We study large batch size training through the lens of the Hessian operator and robust optimization. In particular, we perform a Hessian-based study to analyze exactly how the landscape of the loss function changes when training with large batch size. We compute Hessian spectrum without approximation by extensive experiments on multiple networks show that saddle points are not the cause for a generalization gap of large batch size training, and the results show that large batch converges to point with noticeably higher Hessian spectrum. We show that robust training allows one to favor flat areas. So basically what these people are saying is that empirically we've observed that training a deep network with a large batch size in stochastic gradient descent leads to poor, or not poor, to worse test performance. And the question is why? So they claim that this is because the optimization tends to converge to non-flat minimum. So what's the importance of this paper? Again, it shows to you that people believe that somehow the spectrum of the Hessian or the notion of flat minima is related to generalization. This is another paper by Jastrzębski. Does anyone know how to pronounce this? Jastrzębski. No. Surely there's a person here who can pronounce it. I know Stanislav. That's easy. So they investigate the the dynamical and convergent properties of stochastic gradient descent applied to deep networks. They characterize the relation between learning rate, batch size, and properties of the final minima, such as width or generalization, et cetera, et cetera, et cetera. And then they talk about how learning rate, batch size, and gradient covariance influence the minima found by SGD. And again, they care about flat minima. So this is just another example of people who care about the flatness of the minima. Now, besides this, here's yet another example. So I won't go into detail here, but basically this is a paper that proposes an algorithm which is different than SGD, which is designed to find minima which are flat. So they're inventing a new optimization algorithm that's supposed to find flatter minima. Now, I mentioned that the Hessian is also significant for optimization, right? Not only predicting generalization. And indeed, in the literature, there's quite a few works which are trying to speed up the training of deep nets by somehow utilizing the Hessian. And one of the prime examples is actually coming from U of T by Roger Gross. He has a series of works on this, where what they're essentially doing is they're preconditioning the gradients by the Hessian. So they're using the Hessian information to essentially make the gradients better behaved. So essentially, if you have a landscape that looks like this, if you do gradient descent, it will take a long time to converge. But what you can do is you can essentially apply some, it's called, I guess it's called something like a Newton method, where you're essentially transforming the landscape to make it much more isotropic, right? And then convergence on after this transformation is going to be significantly better. So again, this is this paper and these slides are trying to show you that people care about the Hessian. And there are several works that they did, but I won't go into detail. Okay, so this is kind of a short literature review that's showing to you people care about the Hessian. So what do we know about the Hessian? So in one of the previous lectures, I've shown you these plots where we've seen different measurements of the spectrum of the Hessian. And what we've observed is that the spectrum of the Hessian has this bulk and outlier structure, right? Now, what I didn't tell you at that point was that all of these measurements were done in very simple networks and data sets. So if you look, for example, at one of the examples is by Dufin et al. They look at the MNIST and CIFAR data downsampled to 10 by 10 pixels. And if you look at the one of the measurements by Sagun, they considered a 100-dimensional Gaussian mixture model with a network with 5,000 parameters. So these are essentially very small scale toy problems, right? So those of you who have done homework 7, right? Did you notice that in homework 7, we're calculating the spectrum of the Hessian on a very small network, right? And we're calculating it on a data set which was significantly downsampled. We just chose a small subset of the data set. And also we downscaled the images. Why did we do all of that? Because it's very hard to calculate the spectrum of the Hessian if the Hessian is a very large matrix. And so I also showed you these measurements at scale. So this is, for example, for VGG11, and you can scale it to, even larger data sets and architectures, which essentially measure the spectrum of the Hessian for real cases, right? And the question that you should ask yourself is, how is this even possible? Like, how can you calculate the spectrum of the Hessian for such large networks and data sets? So how does one make measurements at such massive scale? So the first thing you might think to do is basically what we did in homework 7, sorry, homework 7. So in homework 7, we just used out of the box SVD. So you calculate the Hessian explicitly, right? You calculate the matrix, the Hessian, and you do it by calculating each entry in the Hessian, calculate each entry, and then you just apply an SVD on this and you get the eigenvalues, right? Or eigenvalue decomposition. But this obviously doesn't scale to networks which have lots of parameters, right? So one would like to do something better. So what would be the next thing you might consider doing? The next thing you might consider doing is using something like the PAR method. So what is the PAR method? The PAR method is an iterative algorithm where you initialize V0 to be some random vector, and then you just calculate vk plus 1 is equal to hvk divided by its norm. Is everyone familiar with the PAR method? I should ask. Not familiar with the PAR method. So the PAR method is an algorithm. Okay, let me do a one-line proof for the PAR method. Imagine if you take a matrix H and you keep multiplying by H. So imagine if you do something like H times V, right? What would happen as a result? If you keep multiplying a bunch of H's, it's equivalent to doing an eigenvalue decomposition and then taking lambda to a power of how many times it is. Let's say it's K times U transpose, right? Do you agree? So this is just by standard results in linear algebra. And then notice that if you take lambda to a power of K, what's going to happen is that as all the eigenvalues except the top eigenvalue are just going to become insignificant. They're just going to become very small. So here's an example. Imagine the eigenvalues were 10, 1, and 0.1, right? So this is capital lambda. And imagine we take this to a power of 100, right? Then 10 would become 10 to the power of 100, which is a huge number. 1 would become still 1, and 0.1 would vanish. So the dominant eigenspace would be the top eigenspace, right? Does that make sense? So if you keep multiplying by the matrix many times, you just eventually are going to converge to the top eigenspace. And so this is literally what this algorithm is doing. You do vk plus 1 is h times vk. Now, the reason you need to normalize all the time is because you don't want to blow up in norm, right? If you could just keep multiplying by the vector might blow up in norm. So you just keep normalizing it. And as a result, you keep having a L2 normalized vector. Does this make sense? Or was this a horrible explanation? I see a small node. A small node to a horrible explanation. It's like collapsing, I'm just kidding. It's like collapsing the whole space into the eigenspace of the largest eigenvalue, right? Yes, that is exactly right. Yes, yes, yes. That is exactly right. Once you know the top eigenspace, you can mod out then. What does it mean mod out then? Do you mean you can remove it? Is that what you mean? Oh yeah, you can remove it. Yeah, you can. So if you estimate the top eigenvalue and the top, so basically the top eigenvalue is going to, once you have the top eigenvalue, you can indeed deflate that eigenspace. Because if you know that the top eigenvalue, let's denote it by V infinity, then you can calculate V infinity transpose A h times v infinity, that will give you lambda. And then you can do something like h minus v minus lambda times v infinity transpose. Is that what you meant, Jack? That is correct, Karen. Yes, that is correct. It will give you the vector in the eigenspace with the top eigenvalue. That is correct. And then you could hypothetically take this top eigenvector and you could just calculate the eigenvalue by calculating this thing, right? We cannot hear you, Karen.
Sorry, talking to myself. But okay, so what if there's more stuff in the eigenspace though? Like what if it's of degree 2? Or
when you say it's of degree 2, do you mean there's 2 eigenvalues, or do you mean the top eigenspace is of
dimension 2?
Is of dimension 2. So in that case, you would just converge to a vector in that subspace.
So, but then we couldn't, we would have a bit of a tough time removing that eigenvalue from H, right?
Like that is correct. Yes, yes.
Okay, I see.
So usually I think when people analyze this theoretically, I think they assume that you just have multiplicity 1. That's usually the assumption you make. You know, if you think about it, in practice, you never actually have multiplicity 2. I mean, on real data, like the probability of you having multiplicity 2 in real data is like 0, if that makes sense. So Neo is asking, can you just project onto the vector and move that component causation symmetry? Yeah, you can do that, but that's not what we're going to do. This is not what we're going to do. So you guys seem to be sold on the first algorithm I proposed, but maybe this is actually a horrible algorithm. So you should wait to see what else I can offer, because there's better things. So basically, this is a horrible algorithm because it only estimates the top eigenvalue. It's not actually very horrible. You know that Google is literally based on this algorithm, like the search engine. Didn't you guys learn about this in like Algebra 1? I taught Algebra 1 and we taught the PAR method. I guess yes, I think maybe it depends on which algebra you do. Okay, so the next algorithm, so this algorithm is horrible because it only estimates the top eigenvalues. So the next thing you might do is called subspace iteration. Subspace iteration is a generalization of the PAR method for a subspace of k eigenvalues. So it's basically trying to find the top k eigenvalues. And the way it works is as follows. You start with a matrix Z, which is just some random noise. And then you calculate the QR decomposition of the matrix. So QR decomposition is a fancy way of saying Gram-Schmidt, right? So you do Gram-Schmidt, you get Q, you get R. So Q is the the orthogonal basis, and R are the coefficients. And then what you do is you do Z equal to HQ, and then you do another QR decomposition. So I guess if you think about it, maybe it's not the most intuitive thing, just looking at it, why would this converge to the top eigenspace? But let's just say it does converge, okay? So this is another algorithm that you could use. And notice that this algorithm, like many of the algorithms that we'll discuss today, just require a single thing. So both this and the PAR method require a multiplication of H times a vector, right? This is the only thing they require. Why is this significant? Because you don't actually need to construct entry by entry the Hessian. It's enough that you have an ability to multiply by the Hessian. So these are two different things. One is explicitly having access to the linear operator. Another one is having access to a Hessian multiplied by vector, which is significantly more efficient to do than calculating the Hessian. So basically, subspace iteration, think about it as a generalization of the PAR method. Now, there's other algorithms which are also allowing you to calculate the top eigenspace. One of them is called Lanczos, the Lanczos algorithm. So the Lanczos algorithm was an algorithm that was originally used in quantum physics for approximating spectra of infinite dimensional operators. So it's basically an old algorithm. And the beautiful thing about it is that it estimates the top K eigenspace similar to the QR, so similar to the subspace iteration method, but it's very, very fast. So what is K in estimate K eigenspace in subspace iteration? K is the number of eigenvalues that you would like to estimate, Amireza. So let's say you have a Hessian and you would like to estimate the top 200 eigenvalues. So K would be 200. Does this answer the question, Amireza? There is no K in the algorithm. So in this algorithm, the K would be inside the QR decomposition. Inside the QR decomposition, you would have. So if you look at the dimension of Z, Z is going to be, so at the end of the day, Z is going to converge, Q is going to converge to the eigenvectors of that subspace. So it's basically going to be a matrix of size number of parameters times the rank K. So K is implicit in the dimensions of the QR decomposition. So Karen says, I'm still a little turned around about QR. You mentioned it's like Gram-Schmidt, right? Would you mind? Yeah, so QR is literally just a Gram-Schmidt algorithm, which is basically creating a, it's just orthogonalizing. It's creating an orthogonal set of vectors from a set of vectors that you currently have. So let's say you have here Z, which contains in its columns different vectors, right? So what the QR decomposition does is it creates two matrices, Q and R. Q is going to be containing in its columns a bunch of orthogonal vectors, which correspond to the orthogonal vectors in the Gram-Schmidt process. And R is going to contain the coefficients that you get in the QR, in the Gram-Schmidt process. So the coefficients are essentially a three-diagonal matrix because each vector is being represented as function of the previous vectors. So you remember the way Gram-Schmidt works is you keep, every iteration you take a vector and you project away from this vector all the previous vectors, right? So what does it mean for you to project away? It means that your current vector can be represented. So if you have something like, okay, let me draw this. So something like, you have a set of vectors, right? So let's say this would be of dimension P, and this would be of dimension K. So what QR would do is it would do something like this, and then multiplied by something like this. So the first, and I think this would be something like this. So the first vector is just going to be the first. So this is a partial orthogonal, partial orthogonal matrix, which has orthogonal columns, right? And so the first column, so maybe I should name this. So this is going to be Z, this is Q, and this is R, okay? So the first column in Z is just going to be the first column in Q times some scalar. Do you agree with that? Because the scalar is just going to be like 1 over the norm or something. The second column in Z is going to be a linear combination of the first two columns from Q. So there's going to be two scalars here. Does that make sense? Because of the Gram-Schmidt algorithm. And so the Q is the vectors that are being created in the Gram-Schmidt process, and the R are the coefficients that are multiplying the Q elements to create the vectors in Z. Maybe I should have had a slide on QR. But okay, so this answers the question, right? Is there any other questions about QR? So I think we also answered the Amireza's question a little bit better, because now Amireza can see that the number of columns in Z and in Q is going to be K. But I feel like we're wasting too much time on an algorithm that is also a bad algorithm. I guess if I tell it to someone from numerical analysis, this is a bad algorithm, they would probably hate me. So maybe I shouldn't judge algorithms so fast. So another algorithm is the Lanczos algorithm. Lanczos is a different algorithm that also estimates the top K eigenspace. So the top K eigenvalues, it's just done in a different method. So if you want to learn about Lanczos in depth, I would suggest you to read a book by Yusuf Saad. Yusuf Saad is a prominent researcher in numerical analysis who literally wrote a book on, it's not only Lanczos, but Lanczos is a big part of the book. And essentially Lanczos is part of a wide method, a wide family of methods which are called Krylov. Hopefully I'm not misspelling Krylov. How does one spell Krylov? Krylov. Yeah, I did spell it correctly. So Krylov methods, which is a family of methods in numerical analysis, okay? And here is a comparison that shows you how does Lanczos behave versus subspace iteration. Subspace iteration is using the QR algorithm. Lanczos is an algorithm that I have not described yet. And this is the algorithm that you would implement in homework 8, okay? Why is power method not on this graph? Does anyone know? Because it's so bad. Oh Lord. How bad can it be if like Google was created based on the power method? It's not really that bad. It's just that the power method is an algorithm that estimates just one, exactly. So what Jack says, the x-axis wouldn't make sense. The power method is only capable of estimating one eigenvalue, right? So essentially the power method would be somewhere here, because this would be the, you see, this is the number of eigenvalues and this is the number of matrix vector multiplications. So the power method is only capable of estimating one eigenvalue, right? So it would be only on this line. And so the takeaway from this measurement is that Lanczos is good. Subspace iteration is bad. Okay. Now, at this point, you're probably wondering to yourself, what is this Lanczos algorithm that is so good, right? So here's the Lanczos algorithm. So let me explain to you roughly what is this algorithm doing, roughly. Roughly, this algorithm, as I said earlier, is calculating the top eigenvalues of a matrix. Now, the iterations of the algorithm are similar to the power method and the subspace iteration in that they keep multiplying the matrix H, which in our case would be the Hessian, times a certain vector, right? And essentially the point of these iterations is to create a basis that would tridiagonalize our matrix, tridiagonalize. What do the words tridiagonalize even mean? Tridiagonalize means that you take a matrix H and you run the algorithm, it And then the algorithm creates you a three-diagonal matrix, which we call T. So essentially, the algorithm is creating a set of vectors that if you multiply by these vectors on the left and on the right, you get a three-diagonal matrix. Do you see this? Three-diagonal. Three-diagonal means three diagonals. Now, notice that the basis V is of size, the number of parameters times the number of iterations, in this case M, which is basically the number of eigenvalues. And so you can think of V as being a very tall partial orthogonal matrix. Does this make sense? So you're constructing column by column the matrix V. You keep adding one orthogonal vector at a time to the matrix V. And let's say after 100 iterations, you've constructed a basis which has 100 vectors. And then if you multiply this basis on both sides, if you multiply the Hessian by this basis, you get a three-diagonal matrix. Now you should ask yourself, why do we care about this three-diagonal matrix? Does anyone have any guesses? No guesses?
I mean, I'm guessing it'd be much more efficient in terms of computation.
Yeah. So what would you do with this three-diagonal matrix?
You diagonalize it, or
Yeah, you just diagonalize it. So you just calculate basically the eigenvalue decomposition of this three-diagonal matrix, and then you get M eigenvalues, right? So M is going to be significantly less than P. So basically, instead of getting, let's say, 10 million eigenvalues, you would get 200 eigenvalues or 100 eigenvalues, right? Now, given these eigenvalues, you can then create an approximation of the spectrum. So imagine that you got this eigenvalue, this eigenvalue, this eigenvalue, this eigenvalue, this eigenvalue, this eigenvalue, and you're trying to approximate the spectrum of the Hessian. So what you do is you essentially create a Gaussian bump at each one of the locations of these eigenvalues, right? A Gaussian bump means like a small bump, which is centered at one of the eigenvalues of the three-diagonal matrix. And the magic is that these Gaussian bumps have to be weighted by a special number which is related to the eigenvectors. So there is some special weighting that you need to assign to these Gaussian bumps. And after you assign this special weighting, you get a weighted sum of Gaussian bumps that creates the beautiful approximation of the spectrum that I'm going to show you. So this was a lot to process. Does anyone have questions? A lot of information was provided. So it's very hard, to go into details because explaining each one of these things would take an extremely long time. So I'm giving you a taste. And if a person is interested in, for example, what is a Krylov subspace method? Who is the Lanczos person? And if a person wants to figure out whether this is black magic or not, then the person can read the book by Yusuf Saad. How would this work for infinite dimensional operators? Can you provide some intuition about this algorithm and why Phylando should converge to the real spectrum? So I don't have any intuition that I can provide for why it would converge to the real spectrum. There are theoretical results that analyze the convergence of this method to the real spectrum. but I'm not going to discuss them. So for example, if you look at the paper that I cited here, this paper, you could see references that would show you, you know, at what rate do you converge to the real spectrum. But essentially, the most important thing to understand is that we're creating a basis V, or a partial orthogonal matrix. If you multiply this partial orthogonal matrix by H, you get a small, I should have added the word small, a small three-diagonal matrix. I guess it's not here, it should be here. Small three-diagonal matrix. And the eigenvalues of this three-diagonal matrix are approximating the eigenvalues of the original matrix. The algorithm just gives you m random eigenvalues of H. So no, they're the top eigenvalues. That's a good question. I should have emphasized that. It's the top eigenvalues. Should the correctness of these algorithms be immediately clear? No, I didn't even explain properly the steps of the algorithm, right? So it's definitely not immediately clear. So the reason I cannot explain to you clearly the steps of the algorithm is that, again, this basically there's methods by which you can calculate the eigenvalues of a matrix. And there is a special family of methods which are called Krylov methods. And then in those methods, you have something called the Arnoldi method. And the special case of the Arnoldi method is this Lanczos method. But we do not have time to make, you know, to review all of these topics. So we will believe in Lanczos. Lanczos is a person, by the way, you know, he's a famous, what was his name? His name is, he had a cool name. Oh yeah, Cornelius Lanczos. Cornelius, Cornelius, a really cool name. So, but the intuition of this algorithm is that it's doing something. What do you mean, no such thing as free lunches? Oh, free, okay, got it. So the intuition, yeah, I understood. The intuition of the algorithm is that it's in some sense similar. In some sense, it's similar to a Gram-Schmidt algorithm, in that you can see that we keep multiplying V by the Hessian, and we keep subtracting some type of a projection every time. So there's something here that's very much similar to a Gram-Schmidt operation. I should mention something that is important, which is that if you look carefully in the homework, let's say homework both 7 and 8, notice that each time that you multiply the Hessian by the vector, you need to calculate something like the sum of the second derivative of the loss with respect to the parameters for a given example, xi, right? And so this iterates over the whole data set. So this is the Hessian, and this is multiplied by a vector. So the complexity of this algorithm, like one multiplication by the Hessian, requires you to iterate over the whole data set, right? So it's like one epoch of training. So the runtime complexity is that you iterate in each iteration of Lanczos by the whole data set. Also in subspace iteration, in each iteration, you need to multiply by the Hessians, you need to multiply, so you need to iterate over the whole data set. So we're talking about quite heavy computations, right? In general, you think of matrix vector multiplication as something that's very simple to do. But in the present case, your matrix is a summation of a bunch of matrices. So you need to iterate over the whole data set just to do one matrix vector multiplication. And the memory complexity of the algorithm is actually equivalent to just storing 3 models. So why is that? Notice that the steps of this algorithm require you to save a vector which is called vnext, vprev, and v. So there's 3 variables you need to store. Each one of these variables is of size the number of, let's say, rows or columns in the Hessian. So it's the size of your whole model, right? It's a very large vector. But because we need to save only 3 vectors, it means that the memory complexity is rather small. Does anyone else have any questions about the Lanczos algorithm before I proceed? I didn't really explain what is the Lanczos algorithm, but I think I gave the important ideas.
I've got a question.
Mhm.
On the next slide, you said you have to sum over the entire data set.
Yeah.
Could you just sum over a mini batch and take that as an approximation to the full value?
No. Because a mini batch is going to have a very small number of eigenvalues associated with it. So imagine you have a mini. So basically, the rank of a Hessian of a mini batch is basically, if you do here a summation over, let's say, B, right? And so the rank is going to be proportional to B. So if the batch size is like 100, you're going to get just 100 eigenvalues or something proportional to 100. Do you see what I mean?
I don't see why it's proportional to B, because couldn't any one of these matrices be full rank?
No.
Why is that?
Because the second, okay, so they can not, I guess I'm thinking about the Fisher information, but you're thinking about the Hessian. Yes, if you think about the full Hessian, can it be full? I was thinking about the Fisher information matrix. In the case of the Fisher information matrix, this is, you cannot do this. In the case of the full Hessian, I guess you could possibly do it, maybe, yeah. But I don't think you want to do it, because then you get some type of a, instead of getting the true Hessian, you get some strange quantity.
Well, don't you get like an estimate of the, as you take that in expectation over all the mini batches, you'd get the...
Yeah, I don't know. I actually even never tried to look at the Hessian of a single batch. Maybe it would be interesting to try that, actually. I never tried that. Interesting question. Yeah, I never tried. Okay, so as a result of this ability of approximating the Hessian of large models, we saw that many people were interested in studying the spectrum of the Hessians. So you see how around 2019, there were many different works that looked at the spectrum of the Hessian. And so what we've seen is that the Hessian in smaller models had this bulk and outlier structure, but also in larger models, there was a bulk and outlier structure. And in fact, there was one of the more interesting works was by Ghorbrani et al., where they studied what is the effect of batch normalization on the spectrum of the Hessian. So imagine you have a network which has batch normalization layers, and imagine you have another network which does not have batch normalization layers. And imagine you compare the Hessian of the two networks after training. So what they found out is that the Hessian of a network with no batch normalization has outliers. But if you do have batch normalization, it seems like the number of outliers is, it seems like the big outliers kind of disappeared or something like that, right? And so what this shows to you is one use of being able to approximate the spectrum of the Hessian is you can do comparative studies. Here's the Hessian with this thing, here's the Hessian without that thing. Let us ponder, why is there a difference? Are you pondering why is there a difference between the two spectrum?
Sorry, is this at the end of training or?
The end of training, yes.
Okay.
Yes. So you are pondering. So, okay, so the summary is that you can measure the spectrum of the Hessian of modern deep nets at scale. You do it basically using the Lanczos algorithm. The Lanczos algorithm is reducing the Hessian to a small three-diagonal matrix. We calculate the eigenvalues of the three-diagonal matrix. We create Gaussian bumps. We weight the Gaussian bumps, sum them, and we get an approximation of the spectrum. This is the summary. And we see that the spectrum of modern deep nets show bulk outliers, negative eigenvalues. And we also see that the top outliers seem to be suppressed as a result of batch normalization. And with this, we are ready to proceed to the last lecture on this topic. What's wrong with this screen? Okay, so what I'm going to do now is I'm going to answer Amireza's question. Amireza was asking, what is the relation between the spectrum of the Hessian and all the other observations we've made? Okay, so this requires a bit of expressions, which might be unpleasant. I apologize in advance. So the first thing I'm going to do is I'm going to look at the Fisher information matrix instead of the Hessian. The Fisher information matrix is part of the Hessian. If you remember, there was a formula which says Hessian equal to Fisher information matrix, which I denote by FIM, plus some residual, okay? And we know that the Fisher information matrix is positive semi-definite. Now, here you can see the definition of the Fisher information matrix. You can see there's an average over the data set. There is a derivative of logits with respect to the parameters. And let me specify the dimensions because I find the dimensions to be illuminating. So this is of size P times C. Why is this of size P times C? Because if you're deriving the logits with respect to the parameters of the model, the parameters, there's P parameters and there's C logits, right? Do the dimensions make sense? Make sure you understand the dimensions, otherwise you will get lost in the sea of mathematical expressions. The second quantity that we have is the second derivative of the loss with respect to the logits. So this is a C by C, a C by C matrix. And the last matrix is just the transpose of the first one. So it's C times P. Okay. Now, if you remember, if your loss is the cross entropy loss, then the second derivative of the cross entropy loss with respect to the outputs of the network is essentially the Hessian of the multinomial logistic regression model. Does anyone remember problem set? Oh, I think I ruined my trivia question, the most important trivia question. Okay, so does anyone recognize this expression? I'm sorry for spoiling the trivia question. Does anyone recognize this expression? Do you find this recognizable? Where do you recognize this from, Justin? Where do you recognize this from? Okay, okay. So this was a ruined trivia question. I apologize. So indeed, this is just homework one, problem set one. In problem set one, you were asked to calculate the Hessian of multinomial logistic regression. And this is literally the expression that hopefully you have gotten there, right? So this is just calculating the second derivative of the loss with respect to the output of the network, with respect to the logits. Now, we can plug this equation, into the previous equation. So we can plug this instead of this. And then we get these expressions. So we get df to d theta, which are the derivative of the logits with respect to the parameters, times this expression, which I took from here, times the first expression transpose, right? Now, at this point, there is a trick that's being used. So one can prove very easily even that if this expression is diag PIC minus PIC transpose, then it's equivalent to the sum over C prime of, let me write it more clearly, sum over C prime of PICC prime YC minus PYC minus P transpose. What do all of these symbols even mean? So PIC is the vector of probabilities of softmax probabilities, which are C-dimensional, right? It's C numbers that sum to 1. PICC prime, which appears here, is just the C prime entry of PIC. So it's a scalar. YC minus P. So P is supposed to be PIC. Let me add here an I and a C. So PIC, you know what it is. Again, it's the softmax probabilities. And YC is just the one hot vector, okay? So it's just a very simple algebraic identity, very simple. Now, here it's written more clearly. I have a horrible handwriting, which is why I try to print whatever is possible using LaTeX. So here you can see written using proper fonts. And so it's just the sum over PC prime, then YC prime minus P. Oh, here it should have been YC prime. Sorry for the mistake. YC prime minus the probabilities times YC prime as probability transpose. Does anyone have any questions about this expression? So this is a, oops, this expression is PICC prime. And this is just a algebraic identity that's not worth spending your time to prove it. Not worth your time. I did it for you, so you don't have to do it. Now, what I'm going to do next is I'm going to look at the following expression. Take this expression and multiply it by this expression. So I remind you that df to d theta transpose is of size p times c, and yc prime minus p is just a c-dimensional vector, so it's c times 1. And I'm just going to multiply them and see what happens, okay? So here's, again, what I just highlighted in the previous slide. So I'm just going to multiply them. Now, notice that the YC prime minus P is actually just the derivative of a multinomial logistic regression. So it's just the derivative of the loss with respect to the output of the network, with respect to the logits. Does anyone recognize this from somewhere? Do you recognize this expression? Have you seen it in your past? Non-distant past. Where have you seen an expression which subtracts a probability from a one-hot vector? It should be actually the probability minus the one-hot vector and not the other way around. I think there's a minus missing. Where have you seen this? In your non-distant past. Have you seen this anywhere? Notice that this is just the derivative of the cross entropy loss with respect to the logits of the network, right? With respect to so it's the derivative of the cross entropy loss Where have you seen the derivative of the cross entropy loss? Where have you seen it? Yes, it is homework 1. I feel like everyone's just not responding. Yeah, it is homework 1. Yeah, that is correct. Because in homework 1, you calculated 2 things, right? The derivative of the cross entropy loss and the Hessian of the cross entropy loss. So here we're looking at the derivative of the cross entropy loss. In the previous slide, it was the Hessian, right? So anyway, the only thing that's strange here, the only thing that's strange is notice that there is a YC prime here, right? YC prime is a one hot vector which has 1 in the C prime location. And that's a bit strange because we're talking here about an example from the Cth class, right? So it's like you're labeling your data incorrectly for some reason. Now, notice that in light of this expression, if you just plug, instead of this, if you just put this here, right, then you get this expression right here. So this is the derivative of f with respect to theta, which I copied from here, multiplied by the derivative of the loss with respect to the logits, which I copied from here, right? And now notice that using just the chain rule, which we all love and cherish, this is equal to the derivative of the loss with respect to the parameters of the model. But what is strange about this derivative? This is a very strange derivative, right? Because this is a derivative of a loss with respect to the parameters of the model. So you might say, oh, we like derivatives of the loss with respect to the parameters of the model. These are the derivatives that we use to train our model. But I would say, no, these are not those derivatives, because notice, let me use a dramatic color like red, that this thing is YC prime. So it's a derivative of your ith example in the Cth class if you labeled it incorrectly. Does that make sense? Karen, I can see you moving your lips, but I cannot hear you, the result of the movement. It was like, I think it was what? That is best. Okay. Okay. Now, what I'm going to do is I'm going to use the notation GICC prime. G stands for gradient. IC stands from ith example in Cth class. C prime stands for the fact that it's a gradient of the ith example in the Cth class if I were to label it for some strange reason as belonging to class C prime. A bit bizarre, a bit bizarre. Amireza already says that's why you called them extended gradients, since they're useless in training, right? Yes, that is correct. We are going to call them extended gradients. But I wouldn't insult them by calling them useless, because they are in fact useful in the context of the Fisher information, right? So if you look at this slide again, right, do you see how we highlighted this thing multiplied by that thing? So this thing multiplied by that thing is just this gradient, extended gradient that I just described, right? And this thing multiplied by that thing is also an extended gradient. So they are useless in training because they don't appear in training, but they do appear in the Fisher information matrix. So here's what we got thus far. We have that the Fisher information matrix is equal to the average over IC, sum over C prime. This is what we called PICC prime. And then we have this extended gradient times extended gradient transpose, right? Now, if you just use the notation that I introduced, which is GICC prime transpose, then you get this expression. So it's some type of a second moment matrix, right? It's second moment matrix because you get a sum of a bunch of outer products and you have weights. And the weights are just some type of probabilities of softmax. Okay. Now, because there is a 3-index structure here, immediately what you might expect is that we can do a decomposition of this Fisher information matrix into all of these quantities that we talked about in the previous lecture. So you remember in the previous lecture, we said that if there's a 3-index structure, then we can define a rank 1 matrix associated with the global mean, a between class covariance associated with the class means, a between cross class covariance associated with the cross class means, and a within cross class covariance associated with the within cross class covariance. Does anyone remember such a thing in the very non-distant past? I can see small nods of agreement. Okay, now I will not bore you with showing you a bunch of plots except just one. So what this plot shows you is the spectrum of the Fisher information matrix, okay? In the first row. And what you can see is that the spectrum of the Fisher information matrix has 3 parts to it. 3 parts, right? 3 parts. Now, what you can do is you can check what would happen if you eliminate different parts of the spectrum. For example, if you eliminate the between class covariance of the extended gradients, then this bump would be eliminated. So this bump is due to the class means. So here, this is due to the class means. Here you can see if you eliminate the between cross class covariance, if you knock out the between cross class covariance, then this bump disappears. So this bump is due to the cross class means. And if you eliminate the within cross class covariance, then this bump disappears. So you can do again spectral attribution. Attribute different parts of the spectrum to different quantities in this decomposition in the previous slide. So let me just show you what's important to understand. What's important to understand is that we have too many spectra at this point. So here's a summary. This is the spectrum of the features that we talked about 2 lectures ago. The spectrum of the features has a bulk and a set of outliers. The outliers are due to feature class means, right? Then you have the spectrum of the backpropagated errors. The backpropagated errors had a more sophisticated structure where you had a set of outliers due to backpropagated error class means. You have cross-class means, which created this mini bulk, and you had a main bulk. And now we know that the Fisher information matrix has a similar structure. And the question is, how do we relate all of these quantities together? So in order to do that, what I'm going to do, is show you a very simple relation between them. So imagine we have a fully connected layer. A fully connected layer which obtains as input features and outputs pre-activations Z. If you remember, the backpropagated errors are the derivative of the loss with respect to the output of this fully connected layer, and we denote them by delta I CC prime. Okay. Now, one can prove, I will not prove, but it's very easy, that the gradient of the fully connected layer, so basically what I denoted previously by GICC prime, is just the Kronecker product of the features with the backpropagated errors. Okay. So just the Kronecker of the input features and the backprop errors. Now, we know from a previous slide that the Fisher information matrix is a weighted second moment of these extended gradients. So if you just plug in the extended gradients, what you get is sum over pi cc prime of what? HIC Kronecker product with, ran out of space, delta ICC prime multiplied by HIC Kronecker product delta ICC prime transpose, right? Just by plugging in. Now, there is an identity which says that if you have A Kronecker B multiplied by C Kronecker D, it's equal to AC Kronecker BD. So it's a very useful identity of Kronecker products. If you use this identity, you get that the Fisher information matrix, G, is equal to a weighted sum of a feature times feature transpose Kronecker product with backprop error times backpropagated error transpose. So this is an important equation. Maybe this is one of the more important equations in this lecture because it contains all the quantities that we want to relate, right? So you have on the left the feature information matrix, and you have on the right the features HIC and the backpropagated errors delta ICC prime, right? Now notice at this point what I'm going to do is a bit strange. I'm going to try and approximate this matrix. So I'm going to approximate it using the features and the backpropagated errors. And the approximation I'm going to use is by Roger Gross, who I've mentioned in the beginning. So the approximation is called KFAC, and it writes the Fisher information matrix, which is written here, as a Kronecker product of the second moment of features and the second moment of backpropagated errors. Does anyone, here's a question to make sure you're following. Is this equivalent to this or not? Are these two equivalent? Is the Fisher information and GKFAC equivalent to one another? All who believe yes say yay. All who believe no should say nay. Yes, sorry.
Would it be no because we're taking the average or not exactly?
Yeah, it's not equivalent. It's not equivalent. You're correct. It's not equivalent. So Jack is saying one's the normalized version of another. No. So one easy way to see why it's not equivalent is, let me just write it in a simpler manner, right? Here's the identity. If you have sum over xi, yi, is it equivalent to doing sum over xi times sum over yi? Not equivalent, right? And so, because on the left, you just, you know, the xi meets yi when their indices are fixed, whereas on the right, you get all the different combinations. So this is not equivalent. GKFAC is not equivalent to the Fisher information matrix. And GKFAC is an approximation of the Fisher information matrix. Why is this approximation useful? Because you can use this approximation to what's called whiten the gradient. So you can do something like GKFAC, let's say to the power of -12 or to the power of 1, multiplied by the gradient. And then it would basically rotate the gradients and make them more isotropic. Now, there's a property which says that if you want to invert this, you can invert these matrices individually. This is a property of tensor product, Kronecker product, etc. Now, what I'm going to do is I'm going to slightly modify Roger Gross's proposal and I'm going to propose something called CFAC, okay? CFAC is going to do the average over C outside of these expressions. So you can see here the average, the average over C is inside, right? I'm just going to take it outside. So the average is out. Now you might ask yourself, why? Why are you doing that, right? So Amireza is asking, I don't understand why computing these approximations is more efficient. Because if you're trying to, for the moment, let's just calculate them and then it would become clear, okay? I think it's easier than explaining. If it doesn't become clear in a couple of slides, I'll explain that. So these are two approximations of the spectrum, okay? And in the next slide, everything should become clear. Okay, so what I'm doing here is I'm comparing the Fisher information matrix G, which is in blue. Here you can see the spectrum of the Fisher information matrix, with the spectrum of KFAC in orange, and the spectrum of CFAC in yellow. Okay. What can you see in this plot? First of all, you can see that the measurement is done on the last layer of a multi-layer perceptron. You can see that there is a set of outliers in the Fisher information matrix. And you can see that there is a mini bulk, and then there is a bulk, right? That's the first thing you can see. The second thing you can see is that the approximation of KFAC is not approximating correctly the top eigenspace or the mini bulk, right? Because it's just a different distribution. Do you see it's different, non-overlapping? And you can also see that the approximation of CFAC is correctly approximating the top eigenspace as well as the mini bulk, right? So this is just for a single layer. Let me show you what happens if you look at all the layers. So here's the measurement for all the layers. So each row here is a different layer. So in the previous slide, we looked at the last layer, which is this row. Now you can see at all the layers. So for example, here is layer number 6 out of 8. You can see that KFAC is approximating the spectrum not well, whereas CFAC is approximating the spectrum well, right? And you can see the same thing happens for other data sets. So this is for Fashion MNIST, for example. Again, you can see a good approximation of the spectrum versus here there is a bad approximation of the spectrum, right? So KFAC is not approximating the Fisher information well. And you can see the same thing for CIFAR 10, except in CIFAR 10, CFAC becomes a bad approximation also in shallower layers. Does GCFAC retain the number of outliers in all cases? When you say all cases, do you mean in all data sets? Yeah, so as you can see here, it does seem to be doing that, right? You can see that the outliers are matching very well. Here you can see there seems to be some deviation, so it's not perfect, but you can see it's definitely better than KFAC. So with this in mind, it is time for us to answer, finally, Amireza's question, okay? So here's the answer, 2 hours later. So the answer to Amireza's question is, here's the spectrum of the features, here's the spectrum of the backpropagated errors, here's the spectrum of the Fisher information matrix. If you have the Fisher information matrix is a Kronecker product of the features and the backpropagated errors. So you have a Kronecker product of 2 matrices. If you do a Kronecker product between 2 matrices, it's kind of like creating a Kronecker between the subspaces, right? So hopefully you have intuition about tensor products from some courses that you did in your distant past. And so essentially, the features have a set of class means which are being chronicled by the class means of the backpropagated heirs. And after they're being chronicled, you get the outliers in the feature information matrix. So if we denote this mean by mu c, and we denote this mean by delta c, and we denote this mean by gc, right? Then the simple equation is gc is equal to mu c chronicle delta c. So all the class means are in fact related to each other. And similarly, the class means in the features are being chronicled by the cross-class means in the backprop heirs to create the mini bulk in the feature information matrix, and the same about the bulks. Does this make sense? Amireza, are you satisfied with the answer to, okay, Amireza is already asking a question. Should we expect a slower convergence for feature information matrix comparing to features and backprop heirs? I'm not sure. I'm not sure. That's a hard question. That's a question for another lecture. Oh, okay, Amireza is satisfied. Amireza, I dedicate this lecture to you. I should have written at the beginning, dedicated to Amireza. Okay. I just want to show you some intuition in this equation. So here's one way in which you can see why CFAC is better than KFAC. If you look at the CFAC approximation versus the KFAC, in KFAC, this quantity has a set of class means, and this quantity has class means, right? So there's going to be a feature here of a cat and a feature of a dog, and here you're going to have a backpropagated heir of a cat and a backpropagated heir of a dog. Now, if you do a chronicle product between these two things, you're going to have a feature of a cat meet a backpropagated heir of a cat, and a feature of a cat meet a backpropagated heir of a dog. But dogs and cats should not be chronicle product together. This sounds like something that should be put on a t-shirt, you know? Cats and dogs should not be chronicle together. Now, in the CFAC approximation, what happens is that the cat is only being chronicle producted with the dog because the average over the classes is put outside. And that explains, hopefully, why CFAC is significantly better at approximating the spectrum. So you can, so for example, here you can indeed see that KFAC is not approximating correctly the top eigenspaces, whereas CFAC is, because cats and dogs do not meet in CFAC, but they can meet in KFAC. Okay, so at this point, I would like to remind you that the Hessian is equal to the feature information matrix plus some residual, right? And so essentially the Hessian, you can actually calculate the spectrum of the Hessian and compare it to the spectrum of the feature information matrix and the residual. And if you do that, you see that the feature information matrix is positive definite, as we expect it to be. And it has a set of outliers, as we expect there to be. And these outliers are simply inducing outliers in the Hessian. And the reason why the Hessian is, has a distribution here which is symmetric around the origin is because the residual has a distribution which is symmetric in the origin. So basically, around the origin, the Hessian is similar to the residual. Once you go away from the origin, it becomes equal to the feature information matrix. And so here's the plot that summarizes the whole structure of the spectrum. So the feature information matrix has a set of outliers which are being inherited by the Hessian. There is a mini bulk which is being inherited by the Hessian, and there is this residual term which is creating this symmetric distribution around the origin, which is creating this negative eigenvalue. values. This is the meta plot that combines everything. I should mention that there's one thing which is a bit, notice that when we look here at features, you could either look at features at a single layer or all the layers together, right? So for example, if you were to restrict your features to the last layer, we know that due to neural collapse, the class means would be significantly larger than the bulk. So this thing would be very small. This thing would be much more dominant. And in the last layer, the backprop errors would also have the same thing. So the class means of the backprop errors would be significantly larger than the rest. So basically, we just have some low rank matrix here, low rank matrix here, creating a low rank matrix feature information, which would create a low rank matrix in the Hessian of the last layer. So you can see how neural collapse in the features would eventually create some outliers in the Hessian. If there were no neural collapse, if the class means were not larger than the bulk, then you would just have no outliers here, no outliers here, no outliers here, and no outliers here. Right, so the last comment I would like to make is that, as I mentioned previously, Gorbani and co-authors showed that the Hessian tends to have outliers which are suppressed if you have a batch normalization layer. And you can actually understand why that is the case, because a batch normalization layer, essentially what it's going to do is subtract the global mean from the features. You can actually prove that. We will not prove it, but you can prove it. And so essentially, a batch normalization layer is just going to subtract the global mean from the features here. So what does subtracting a global mean do to the spectrum of the features? It's just eliminating the top outlier, right? And so if you're eliminating the top outlier from the features, then you're in effect eliminating some outliers in the feature information matrix, and therefore you're eliminating outliers in the Hessian. So this is written here. So if you have a top outlier in the features due to the global mean, then that is creating C outliers in the feature information matrix, and that's creating C outliers in the Hessian. And so batch normalization is just going to eliminate all of these, and therefore you're suppressing the outliers. So let's check your understanding. Based on this information, does this mean that we've suppressed the class information in the spectrum of the Hessian? So after you apply if you have batch normalization layers, does it mean that you have no class mean information because the outliers are suppressed? It does not mean that, because a batch normalization layer is basically going to subtract the global mean from the features. And so it's not going to eliminate the class means, just the global mean. And the global mean is in some sense insignificant. So it's like removing a part which is insignificant. If you have a classification problem, you shift all your features by a global mean, it doesn't actually do anything if you think about it. The class mean information is still present everywhere. It's just that the class means don't have a global mean, so they're going to be closer to the bulk, closer to the bulk. It's the top C eigenvalues, but it would also, yeah, it could be also C times C minus 1 eigenvalues. So maybe I could just illustrate this. Here's a spectrum. Here's a set of class means. If you subtract the class means, these outliers are just going to be slightly smaller, right? Because you're removing energy from the top eigenspace. So it seems like we're out of time. So here's the summary of this whole topic. Next time, we're going to move to a different topic. So the summary is that there is a boomlet in DeepNet spectra. There is patterns which are ubiquitous, such as outliers, minibulks, and bulks, which are manifested in modern successful deep nets. We saw that there is a two-index structure in the layer-wise features, which call the global mean in the features cause the largest outlier. The C-class means caused the C-1 outliers, and there was a deviation around the means, which caused the bulk. There was a three-index structure in the layer-wise backprop errors. We saw that there is a global mean, which was creating the outliers. C-class means causing the C-1 outliers. C-squared cross-class means, which caused the mini-bulk. And we saw how the structure in the features and the backpropagated errors induces the structure in the gradients, GICC prime, the feature information G, and the Hessian. That is the end of the lecture. Thank you for joining, and I will stay for questions.
Hi, can I ask a question?
Yeah, of course.
What is the, I mean, in the paper where they showed that you can arbitrarily change flatness and it doesn't change classification, what was their working definition of flatness?
They showed that they considered the several. If I remember, something like 3 definitions. I think one of them was the most intuitive one, which is the largest eigenvalue of the Hessian.
Okay, because I'm wondering from what you've said, right, from your spectral decomposition, it seems like the largest eigenvalue would be attributed to the global mean, right?
Unless you're using batch normalization, in which case it might be not the global mean.
I mean, like these top ones can be eliminated if you project by like mu sub g transpose, right?
Mm-hmm.
So I wonder if the reason why that's uncorrelated to generalization is because like it's just the global mean, it doesn't contain class information, right? Like if you use that notion of flatness.
Yeah, that's one observation that's correct. Yeah. That's one thing that's correct, yeah.
So maybe if they looked at like these middle ones, that might correlate to generalization.
Yeah. Like if you look at the class mean information instead of the global mean.
Yeah.
But the thing is that if you use batch normalizations, presumably removing the subspace of the global mean, if you do things carefully.
Oh, I see. Right.
But I'm not sure if they did things carefully. Like you need to be very careful in your experiment. If you're very careful in your experiment, you could eliminate the global mean using batch normalization. But I should mention that there's definitely a good point in what you're saying, in that the thing that should correlate with generalization is the class mean structure, and more specifically, the ratio of the class means to the bulk, which is basically the signal to noise ratio, right? Yeah. But I should mention also that all of these measurements are done on the trained data, right? And the question of generalization is basically the question of how do the same quantities look like when you move to the test data?
Right, yeah.
And that's a much less trivial question.
Okay. Thank you for answering the question.
How important is the residual term in the Hessian? Is it a good idea to approximate the Hessian by dropping the residual, or is that not ideal? So if you look at the KFAC optimization algorithm, the KFAC is replacing the Hessian by the Fisher information matrix, and then it's approximating the Fisher information matrix through the chronometer of the features and backprop errors. And it seems like their optimization is, working. So from their paper's point of view, it seems like dropping the residual term is not a bad idea. Beyond that, I'm not really sure. Essentially, if you remove the residual term, it's equivalent to approximating the landscape using a positive definite matrix, right? It's kind of like creating a quadratic ball instead of because the feature information is positive definite, right? So I think people like using the feature information because of its positive semi-definiteness. But I haven't seen anyone who really answered your question, Stephen, beyond what I just said. It does seem like it would be damaging. Yeah, it does seem like it would be damaging. I agree with that. Yes. Yes. There's one paper that studied the negative eigenvalues. It was by a person from Leroux, was his name, in the Haitian. And there was another person who studied the spectrum, like theoretically analyzed how large is the residual in the context of the neural tangent kernel, which I'm going to discuss in the next lecture. But I'm not sure if I saw anything that's illuminating really whether the residual is important or not important. I don't know. Open question. Anyways, I think I cut you out in the middle.
Yeah, I can ask a question.
Yeah.
Can you bring the previous slides, the one which had the plots for Gorbani and Krishnan for effect of batch normalization?
Oh, that's in the previous slide. Yeah.
I was wondering, based on only these two plots, how can you say that still the information for class means are, I think the information is hidden a bit in the bulk after batch normalization. And maybe you cannot extract it.
You can definitely extract it. I'll tell you why. Because the information of the class means in the Haitian is just due to the class means in the features and the backprop errors. So here's a trick you can do. Take your features and take your labels and calculate feature class means mu c. Calculate the Kronecker product with your backprop errors, let's say delta c. And then just calculate this quantity. This would give you the subspace of the class means. So you don't need your class mean information to be larger than the bulk for you to estimate it. That's the first comment. The second comment is that there's no real way to know if, these quantities here, maybe these are like the outlier, maybe this is like the class information, right? It's possible.
Yeah, it's possible.
And also there is nuances about their measurement which are non-trivial to explain and which might make their spectrum significantly more complicated and might hide patterns. I can go into the details, but I'm not sure if you want me to go into them.
Nice. But I think also in the notions of information theory, when you pad the information with noise, you're removing some information. And I think here, when you're suppressing these class means, they are padded or mixed somewhere inside the bulk. And only based on these plots, I'm saying that you cannot extract the class information. But yeah, there are several ways you can do.
Yeah, I see what you're saying. Yeah, definitely. But I like thinking in terms of simple. If you imagine a simple mathematical abstraction of this measurement, then here you have some type of a bulk and outliers, and basically, if you subtract the global mean, you're just reducing the energy of the subspace, right? Like if you project away a rank 1 matrix of global means, it's just making this matrix have a smaller energy. So it's just shifting it to the left, right? But the information that you're projecting away is useless information because it's just the global mean. So I don't think that the fact that the outliers become closer to the bulk indicates that you're harming your classification in any way. Does that make sense?
Yeah. Thank you.
Can I ask a question?
Mm-hmm.
About the eigenvalue calculation, the Lanczos algorithm is computing like the top k eigenvalues, right?
Mm-hmm.
Does anyone compute the bottom k eigenvalues, and is there anything interesting going on there?
Yeah, so there is a paper by Nicolas Leroux. I don't know how to pronounce his family. Leroux, and he investigated the bottom eigenvalues. One easy way in which you can approximate the bottom eigenvalues is if you do something like, let's see. So if you just, if you do like minus h, right? If you calculate the eigenvalues of minus h, then the top becomes the bottom becomes the top, right?
Yeah.
And then you can just use Lanczos on that matrix.
Yeah. But is anything interesting happening with those eigenvalues, or like what do they look like? Do they have outliers?
I think that they do have outliers in the beginning of training, but I don't think anyone really investigated that. I think that's what Stephen was asking earlier, which is the negative eigenvalues are the directions in which your loss is going to decrease, right? So it does make sense to look at those directions. Yeah, I'm not aware of anyone who did any investigation of them beyond Leroux. And I don't quite remember what was his conclusion. I think it was a short paper. I don't remember if they extended it to a longer paper.
Okay. Thanks.
Hi, Professor. Can I ask about something about homework 7?
Yes.
Yeah. So I'm just confused about the like in task 1, the function that touch.autograd it does not return matrix, right? It only returns tensor, right? So
Torch autograd grad returns a list of tensors.
A list of tensors.
You can just print it.
Okay. So the thing that confused me is that in part 2 you say the calculate the gradient of gradient which is the Hessian.
Yeah.
But then the text 2 you just take the column of that Hessian, but text 3 then you just put those columns back.
Yeah.
Like but don't we get the Hessian from task 1 directly?
No. If I remember correctly, task 1 calculates H EI transpose EJ.
Oh, okay.
So it's a single entry in the Hessian.
Wait, single entry of the Hessian. Oh, I see. So you mean it's only a value in the.
Let me make sure that I'm not confusing you, that I'm not lying. Homework 7. Should avoid confusing you. Task 1 says, so task 1 requires you to Hessian vector multiplication. So I was confusing you. Task 1 asks you to calculate this for some vector v.
Okay, so that syntax, what I confused, like using that syntax, you can compute HV, but you can't compute H directly.
Yeah.
Okay.
Because calculating matrix vector multiplication is significantly easier than calculating the Hessian.
Oh, I see.
It's a general theme in life. Like, think about the Fourier matrix versus the Fourier transform. So constructing the Fourier matrix, like if you construct the Fourier matrix and multiply it by a vector, constructing a Fourier matrix would take you a lot of time, like O(n)² right?
Okay.
But applying Fourier matrix onto a vector would take you n log n because of the Fourier trick. Do you know what I'm talking about?
I have some idea.
Some idea.
Okay, I see. So in task 1, if we use the syntax, like the syntax, it has three input. It has like outputs, inputs, and grad outputs.
Yeah.
So for the outputs, we just put in our loss function, and for the inputs, do we just input the parameters of logits, and for the grad outputs, we just put in the vector, right? So it's like
you need to derive the gradient, so you need to put in the gradient in the input.
Yeah, definitely. So first we just calculate the gradient, then we just use that syntax again to calculate the Hessian.
Yeah.
Yeah, I'm just a little not sure. Like for the inputs, do we input the parameters that's in the logits?
No.
Where do we get our input from?
Input is what you're deriving, right?
Yeah.
So what are you interested in deriving? If you're calculating a second derivative is a first derivative of the gradient. So you're deriving the gradient.
Oh, so you're saying the input should be the gradient?
No, the output should be the gradient. The input is what you're deriving with respect to. So those are the parameters, right?
Yeah. So the parameter I was thinking it shouldn't be like just logits dot parameters.
No.
Wait. Is it labels?
No. Think about what you're trying to do. You're trying to differentiate first the loss with respect to the parameters.
Yeah.
And then you're trying to differentiate this with respect to the parameters. So theta are the parameters of the model.
Yeah, but our model here is logits, right? Because like logits equal to model image.
Yes, but the parameters are not the logits. The parameters are the model parameters. Try right. So.
Okay. Just model dot parameters, right?
Yeah, but try to understand why it's model parameters, because the logits are not the parameters, right? The logits are something completely different.
Okay. Just okay. I see. Yeah, I think I have the correct idea. And sometimes I'm just confused about these variables. Like,
I would suggest try writing the dimensions of every single quantity. Like try writing the dimension of the derivative of the loss with respect to the parameters. Try writing the dimensions of the parameters. Try printing the dimensions of the parameters. Verify that all the numbers do make sense.
I see. Okay. Thank you. Thank you very much.
Professor?